lighting won't be such an issue anymore. So we're going on to our Pascal's triangle. We pull down our 1s, 1, 3, 4. I switched colors in the middle of the triangle, but that's alright. 3 plus 3 is 6. 3 plus 1, 4. Carry down our 1. Alright, we have room to do another one. So 5, 10, 10, 5, 1, and maybe we can fit one more in here. 6, 15, 20, 15, 6, 1. Alright, so what does this tell us? I noticed earlier I said that it tells us the constant, right? But a constant is just a number by itself. What it tells us is the coefficient to the term that we're using the expansion from. So in this case, our n equals 2. So we need to find the line that is associated with n equals 2. It starts out at n equals 0. N equals 1. This one for n equals 2. Our constants, coefficients, are 1, 2, 1. 1, 2, 1. Alright, so since the 1 is the same thing as not having anything at all, we see how these are equivalent. So let us finish out the triangle. This one is for when n equals 3, n equals 4, 5. We made it all the way to when n equals 6. Let us try a little bit more complicated example, eh? Let us look at the expansion of a plus b cubed. Once again, this is an identity, specifically identity 6. We already know the answer is a cubed plus 3a squared b plus 3ab squared plus b cubed. So now let's try it with the binomial expansion. So when k equals 0, let's write our a plus b cubed. It's always good to write that. What is a? Well, a is a, b is still b, and n equals 3. So our first term, when k equals 0, we do a to the n, a cubed, b to the k, or b to the 0, which is 1, plus, save room for your coefficients because only the first and last are going to be 1. Take 1 away from the power of a and add 1 to the power of b, plus coefficient. 1 away from the power of a, add 1 to the power of b, plus a to the 0, take 1 away from the power of a, b cubed, add 1 to b. Go back to our Pascal's triangle to find our binomial expansion's coefficient associated with n equals 3. We have 1, 3, 3, 1. Let's add in our coefficients. 1, 3, 3, 1. You see this lines up with this one perfectly. So that is the binomial expansion, and it works for any value of n, any integer of n that is greater than 0. So any positive integer of n. Let's look at one more example with the a's and the b's. This time, let's expand a plus b to the 5th power. Now, we don't have a way to check it out unless we want to go through and do the old-fashioned multiplication. I personally don't, but if you don't trust me, go through and feel free to do it. But we have a to the 5th power, a to the n, times b, 0. 0 is always the first values of k, plus coefficient, a to the 4th power, or n minus k, I'm sorry, with k being 1, and b to the k, plus coefficient, A cubed, k is 2, so b squared, plus coefficient, take 1 away from a squared. Add 1 to b cubed, plus coefficient, b to the 4th, plus b to the 5th. You're always going to end with a to the highest power. Begin with a to the highest power, the power of n equals 5. We're going to write n equals 5. And end with b to the 5th, or b to the nth power. Let's go to our Pascal's triangle. When n equals 5, our coefficients are 1, 5, 10, 10, 5, 1. All right, so if you notice some facts, or you can call them properties, of the binomial expansion, are as you add another term consecutively, right? So this is your first term, your second term, third term, fourth term, whatever's after that plus or minus sign. The power of a decreases by 1, right? So 5, 4, 3, 2, 1. But likewise, the power of b increases. You had 0, 1, 2, 3, 4, 5. All right, so you could almost write those separately. I guess I should have. Let's say this is point 2. All right, point 3. Your signs are different for addition and subtraction. If you have addition going on inside the parentheses, if you're adding two numbers together like you are in this example, then you always have a plus sign. Before each new term, right? Before each new term. Less. All right, but if you have subtraction, so that's a minus b, if that's what it looks like, if you have a minus b, some positive and then some negative, right? Some positive minus some positive. Then you rotate the signs of each term, beginning with subtracting. All right, so let's look at an example of that. Let's do an expansion for u minus v to the power of 6. Here, our a equals u, b is negative v, and n equals 6. So we start out with a, which is u, to our n, times negative v to the 0 power is still just 1. Start out beginning with subtracting. Minus, make sure to leave room for your constant. We'll just skip some space and not underline it anymore. A 6 minus 1, 5, b to the first power, plus, rotating your signs. Let's leave room for our constant here. All right, u to the fourth, b squared, minus, let's leave room for our constant, our coefficient, u cubed, b cubed, minus 1, plus 1, plus, leave room for our coefficient, u squared, v to the fourth power. Why didn't anybody tell me I was putting b instead of v here? Well, a now equals negative b, right? There we go. Yep. Now all of a sudden I put v when I change it to b. Okay. Minus, leave room for our coefficient. 2 minus 1 is just 1. B to the fifth power, and then plus b to n, right? Now, let us use our Pascal's triangle to see what our coefficients are. We're looking for when n equals 6. That's the last line that we did. In that case, our coefficients are 1, 6, 15, 20. Then it repeats, right? It mirrors. So around this 20, it mirrors. You have 6, 15, 20, 20, 15, 6. Now, when n is odd, like when n equals 5, you just draw a line down the middle, and it mirrors around that. When n is even, it mirrors around the center number. All right, so our coefficients are 1, 6, 15, 20, 15, 6, and then 1. My 6 and b's look pretty similar, so we'll probably stray away from using that as an example. All right, now let's look at an example when we have numbers and not